All right, so this video is going to be a little bit different. I'm going to film it on my cell phone. All right, hey people. All right, here's what we're going to do. We're going to do a lab about specific heat. And let's think, first of all, let me give you an example of why specific heat is important. Different materials obviously heat up differently. And let's think about something. Let's think about, I'm just going to throw it out there. We'll just try to keep things important here. Let's talk about dirt bikes. All right, so on my dirt bike, the front brake and the rear brake are both disc brakes, okay? And disc brakes have pads. And when you squeeze your brake, the pads press against the disc. It's just like on your car, right? And that creates a lot of friction, which slows your car down, correct? Why would it be important to use brake pads and discs that had a very, very high specific heat?
Because it gets hot.
Yeah, it gets hot. And if you use the wrong materials, they could catch on fire. They could melt, right? So brake pads and things like that with lots of friction, the specific heat of the objects is very, very important. Does that make sense? Does that make sense, people? All right. So what we're going to do is calculate the specific heat of some metal. We've got aluminum here. This looks like, let's look at the top of that. That's 10, SN. Whoop. We've got copper, and that's obviously copper. And I feel like I had some lead here earlier, didn't I, right? I had some lead. And the last piece here is lead. Here's the lead. So we've got lead, copper, tin, and aluminum. And I know they all look different sizes here, people. I know these all look different sizes, but the fact is they all have the same weight. They all weigh right at 70 grams, and I can prove that to the people at home. I'll show you guys. See that? 66. It seems off a little bit. 67. 69. 70. All right, so they all weigh about the same. Okay, so how are we going to do this? What we're going to do is we are going to check and see how those metals heat up water. All right? Now, what we're going to do in here, people, is we're going to get all of our water boiling, and I would ask you a question, students in the room and students at home. What is the temperature of boiling water? Does anyone know? What is the temperature of boiling water? 100 degrees Celsius. Y'all couldn't hear that at home, but all the students in the class were screamed, duh, Mr. Perkins, it's 100 degrees Celsius, okay? So what we're going to do, people at home, is we're going to take our piece of metal and we're going to dangle it in the boiling water. And if we dangle it in the boiling water for a couple of minutes, we know that the temperature of this metal, when we pull it out, is going to be 100 degrees Celsius. Does that make sense?
What?
Girl, put 100 milliliters in there. All right, so we're going to use 100 milliliters of water. And the water that we're going to use first, we're going to know the temperature, okay? So we got 100 milliliters. That looks good, getting there. Perfect. We're going to get 100 milliliters of water. We're going to put it in a styrofoam cup, which is heavily insulated, right? And then we're going to take our 100-degree chunk of metal and throw it into the water, and we're going to calculate the temperature change. And that's all we need to be able to do to go backwards and discover the specific heat of the original metal. You'll watch it happen, people. So when we're thinking about this, here's a question you need to think about. The 100-degree metal ingot will change the temperature of the water. The metal with the higher specific heat will change the water temp blank. We know we have 100 grams of water in our styrofoam cup. So if we just calculate the temperature change, and we know the specific heat of water is 4.18, and we know we have 100 grams of water, then we can find how much energy was given to the water in our cup. Does that make sense? The only thing we need to do in order to do this is know the before, which is basically 23 degrees Celsius. Know the before and after temperature of the water. So I need everybody right now in the classroom to write down the current temperature of your water. Write that down, your initial temperature of the water in your styrofoam cup. All right? So all we need to do is take our metal, okay? We're going to have it dunked in boiling water. And we're going to dunk it here for like a minute so we know that the metal will get up to 100 degrees Celsius. Then we're going to take our metal and we're going to drop it really quickly into our water. Then we're going to throw a cap on it and we're going to start swirling it around and we're going to see how high the temperature goes. We'll be able to calculate the change in temperature of this water and know how much and know how much energy was given to this water by the piece of metal. That's going to help us do the lab. So right now we're dangling the metal under the water. It's boiling. The metal is getting up to 100 degrees Celsius. Okay? Okay, we've had it in the boiling water for about a minute. And we're going to do a countdown. Everybody ready for the countdown? At the end of the countdown, we're going to put it in the styrofoam cup. And then we're going to cap it and calculate our highest temperature. Ready? 5, 4, 3, 2, 1. Straight into the cup. Throw that in there. Now we've capped it up and start swirling. Now we're going to watch the temperature go up. The metal, hot metal, is now warming up the water. Looks pretty good right here. That's the highest temperature I've seen so far. You got 25.6. That looks pretty good. Yours isn't going to be quite the same, Maisie, because you have so much water, okay? Okay, our highest temperature here was 25.6. And what was your original temperature?
23.
Exactly? Mm-hmm. Okay. So now we're going to do some math here. We're going to find out how much energy was given to the water. So, your water went from 23 to 25.6. So his went from 23 to 25.6. If we subtract those two numbers, his delta T, his water changed by 2.6 degrees. Is that right? And it was water, liquid water, so 4.18. And he had exactly 100 milliliters, or 100 grams, remember that's the same thing in water, in the cup, right? So the amount of energy given to his water is equal to the product of these three numbers, 100 times 4.18 times 2.6, 1,087, that's what we're going to call it. 1,087 joules were given to the water. All right, pause that for a second. So, we know this is how much energy was given to his water. Okay? Now we can work this problem backwards to try to figure out exactly what metal he has. Now we really know what metal he has, but we're going to work the problem backwards. Now don't you all agree that if this was our cup and the cup got hotter, where did the energy in the cup come from? It came from the chunk of metal. So this is our first law of thermodynamics, is that the energy had to come from somewhere. So the energy came out of the metal. So now we can do this problem saying that the 1,087 joules came out of the metal. How much did your metal weigh? Do you remember? Can I see it? I'm going to get yours exactly so we can get a good number. Thank you. We're going to measure this. $70. So we know that we had 70 grams of the metal, right? And let's talk about the change in temperature for the metal. What was the highest temperature of your water?
25.6.
Uh-huh. And then what was the original temperature of the metal?
Original temperature.
Was 100 degrees Celsius. Remember, this is why we had the metal in the boiling water. So the metal changed by 74.4 degrees. So the change in temperature of his metal was 74.4 degrees. Now you guys, your change in temperature will be slightly different, right? But we're solving for his. So let's see if we can get an accurate, specific heat for his metal. 1087 divided by 70 times 74.4. I'm going to calculate that. Divided by, parentheses, 70 times 74.4, close parentheses, equals 0.209. So that's not perfect. 0.209 joules per gram is what we get for yours. And now let's go. Tell us, what was your metal? 10. All right? We can fill heat of 10. I don't have 10 on here. Let's Google it. Ready? Specific heat of 10 is, check it out, 0.21. Right here. So you did yours, and flip back over to here. So you did your, it was perfect. Your lab worked out perfectly. But we're going to have to cut on that. That's perfect.